Okay, so we did the one-dimensional case, and we saw some of the basic ideas: bound charge, internal fields, external fields, polarization. Now let's let things get more complicated. So if you do other geometries, those can lead to non-uniform P, which can lead to great excitement. So we're going to see new things when we let our polarization become non-uniform. All right, so let's just pick another geometry. Let's put a point charge, and I'm going to call it Q free, right? Because this is the charge that creates the effect, QF, Q free, inside a dielectric sphere. Now let's just see what happens. Okay, so dielectric sphere, and there's the point charge. I won't label it because I got to draw a lot of field vectors. Okay, so you know what a point charge does. It makes a field sticking out. And now it's not really that it's making a field and we're putting a dielectric in the field. The dielectric is automatically all over the field. It's everywhere. So if we think about it, we know this is going to make an electric field pointing away because it's positive. So that's going to attract the negative charge, and it's going to push away the positive charge. It's going to create little dipole moments that are going to point out. And then the volume of the dipole moments and the size of the dipole moments will be bigger when you're close to the charge, and it'll be smaller when you're far away from the charge, because the electric field the charge creates is bigger and smaller. So the P, the polarization you would end up with, the dipoles per unit volume, would be big when you're close and get smaller when you go far away. Big when you're close, big when you're close, big when you're close. I could do them with field lines, it would be better, but I've already started drawing vectors, okay? And it gets smaller when you get farther away. And it gets really small when you get really far away. Okay, so that's the P, that's the polarization field inside the material, okay? And it's not quite making it to zero, it still exists a little bit at the surface. So what's that going to do? First, it's going to create sigma B, right? If this thing is pulling negative charge, sucking it towards the positive, if the positive charge of Q free is sucking a lot of the electron clouds in, it's going to leave the outer part positive. It's going to leave a charge density on the surface. And we know the formula for that is P dot n hat. So as long as there's some positive, or as long as there's some P vector that remains on the surface, I drew it decaying too rapidly. Okay, we can draw it like that. There you go. So there's some P field remains on the surface. You dot it with the normal direction, which of course is the same direction, and you get that the charge density on the surface is just the value, the magnitude of the polarization at the surface, okay? But something else happens, and something else happens inside the material. So now let's imagine grabbing a little piece of it that looks something like this, just a little radial sort of a slice, right? So it kind of looks like that. Oh, whoops. I'll blow it up a little bit, kind of like that. Some three-dimensional piece coming out of here. If we looked at it, we'd say, actually, here the P, the polarization field, is kind of bigger on one side than it is on the other side. Right? So if the polarization field is bigger on one side than the other side, what's that going to do? Well, when it's big, it pushes a lot of charge. So if we were to imagine, let's see, is there going to be negative charge on this surface? Right? Polarization's that way. It means negative charge gets pulled this way. So you'll get a bunch of negatives. I'll say 3, 4, 5, 6. I'll draw 6 negatives on that surface because they're being attracted to the positive. But out here, where it's weaker, maybe there's only 3 positives, right? Because the polarization is smaller and it's the same surface area if I drew it right. So this volume, so the volume has a net charge. Okay? It's a neutral material, it's just a neutral dielectric, but net charge is being created within the volume. So it also creates what we call rho B. So volume charge density that's equal to minus the gradient, or minus the divergence of the P field. Okay? So these are general results that you can calculate with a lot of vector calculus and field theory. I'm just kind of giving them to you, but they kind of make sense. You can see how, well, we talked about this one. Let's think about this one for a second. If you're really into field theory and you understood Unit 1, you can kind of see how the divergence of the P field has to do with creating the P field, right? So it is bound charge that creates the polarization field. Or if you just want to think of it as a derivative, right? If you're not as quite into the vector calculus, but you understand this gradient or this divergence is a derivative, you can kind of see the amount of bound charge you get in this little element. If you shrink it down, it's the difference between how much is on this side and that side. It's the difference in P. It's delta P, delta X. So it's a derivative. And this is just a derivative. So whatever level of vector calc you're into, hopefully you can see that that's what goes on. And you might say, how can it create charge if the thing is neutral? And in this case, the answer is they cancel, right? So the amount of surface charge you get, the total amount of surface charge, in this case, would be positive. You're going to leave positive charge out there, and everywhere you go on the inside, this is going to come out negative. So if you were to add all up the bound charge, it would all add to 0, because the thing actually does have to be neutral in sum. Now that we understand free charge and bound charge, now we can get serious, okay? Let's write some serious stuff. There's not going to be any drawings here. This is just serious, this is serious stuff. If free charge is placed near a dielectric and induces bound charge the total uncancelled, I'll say, charge is what? It's just rho total equals rho bound plus rho free. And they could be sigmas if they're surface charges. But let's assume for now that they're volume charges. All I'm saying is free charge is clearly excess charge. And rho bound, that's why I meant uncancelled, right? So the dielectric is neutral, but if its charge gets shifted around, you might have some places where it shows up, either on the surface or in the bulk. That's what we've been talking about. So now we have a statement of the total charge. But now what are we doing? Why do we do this? Okay, I'll do one more. Okay. Why did we do this? We had a dielectric sphere, right? And we're going to put in a charge. I'm not even going to put it in the middle. I'm going crazy, okay? It's going to create a polarization field. You're going to get bound charge in here. You're going to get bound charge on the surface. You got your free charge here. What we really want to do is calculate the electric field. We want to calculate the electric field in the material, out of the material. It's going to respond funny. We want to figure all that out. Well, when you want to calculate the electric field, the most powerful way to do it is Gauss's law, okay? So we're going to take this and stick it in Gauss's law and see what happens. Okay, so whenever you want the electric field, apply Gauss's law. And Gauss's law does not care about external fields and internal fields and who created what and superposition of all those fields. No, Gauss's law just calculates the E field. So we're leaving all those subscripts off. Now when I say the E field, I mean the actual E field. I mean that if we took a test charge and put it in that region and ignored all the molecular structure, F equals QE. This is telling you the force on that test charge. Okay, that's the only electric field that we care about. Okay, Gauss's law. The integral closed surface E dot dA equals what? It equals the charge enclosed over epsilon naught. So here is our total charge enclosed in that surface, rho bound plus rho free. And when those are written as charge densities, you just have to write them as integrals. 1 over epsilon naught, the integral over the volume of rho free dV, plus 1 over epsilon naught, the integral of rho bound dV. Right? That's really just Q enclosed over epsilon naught. Just the two flavors of Q enclosed, the bound and the free. Okay. Now let's write it again. The integral around this closed surface of E dot dA, and we're going to change one of them. Let's leave this one 1 over epsilon naught integral of rho free dV, and then this one, remember what was rho bound? It was minus the divergence of big P. Right, so we could write this as 1 over epsilon naught, the integral of minus the divergence of the P. Right? We're trying to work on this in terms of fields. Okay, and now let's apply the divergence theorem. This is real field theory now. What was the divergence theorem? That was, I always like to say it. How was it I like to say it? The integral of a derivative over a region is related to the value at the boundaries. Right? All the theorems of calculus, that's really what they are. This is the integral of a derivative over a region is related to the value at the boundaries. So instead of this integral of this divergence, which is a derivative in a volume, we're going to turn that into a surface integral of P. That's what the divergence theorem does. So we still got this part the same, the integral around a surface of E dot dA, and we still have this part, 1 over epsilon naught, the integral of the free charge dV. But then the negative sign is going to stay, and it's going to become minus 1 over epsilon naught, the integral of P dot dA. Right? The integral of a derivative in a region is related to the value at the boundary. Okay, we've turned it into that. Well, now if we look, we see that these are the same integral. They're over the same closed surface, and one is E and one is P. So we can bring this over here and say it's the integral around the closed surface of E plus, I'm sorry, so we also have to multiply through by epsilon naught, epsilon naught E plus P plus P, right, equals the integral of rho free dV. So the epsilon naughts went away. And this is actually the useful way to apply Gauss's law to find the electric field. But what we do is we give this a new name. This is what we call D. Ugh, that's a terrible looking D. This is the displacement field. The displacement field has always bothered me. It seems so unnecessary. Why do we need to make up a third field? We already have the electric field, we already have the polarization. Can't we just call this always epsilon naught E plus P? Do we have to call it D? Is there some intuitive meaning of the displacement field? I don't think there is. It's very useful to solve problems, and I'll show you in a minute we'll solve a problem. But I think if you look at Maxwell's original paper, he just labeled the fields A, B, C, D, E, F, G, H. Right? And then he had some nomenclature that nobody uses anymore. And then Heaviside and I think Hertz or someone gave us the modern version. And I think they kept D and called it displacement, but I think of it as it displaces a lot of work you would have to do keeping up with things. That's my definition of the displacement field. So you're going to see in a minute, though, why it's useful. So we could ask, why displacement? Why must we come up with another field? And the answer, I guess, is it makes Gauss's law work inside and outside the dielectric. Right? Because what is it? It's the integral, and that was epsilon naught E plus P. Well, that's basically D. The integral of D dot dA around a closed surface equals the free charge that's causing everything to happen. Right? That's getting pretty simple. So let's look at an example. All right. So let's say we have a charged, charged wire, a rod of charge, a thin rod of charge. And it is the free charge. It's what's making everything happen, lambda F. And then outside this thing is, wire is a solid dielectric cylinder. All right. So let's see, so and this is solid, right? So a dielectric cylinder. And it's really long, so we have all of the symmetries that we like. I'm just drawing it short. Okay. So this is a standard dielectric problem. We have a free charge and induces a bunch of bound charge, all kinds of exciting things happen. But the point of using the displacement in Gauss's law is we don't have to think about those. All we got to do is apply Gauss's law. So we say, well, let's imagine a length of this L that's really long, and let's say it has some radius big R, I guess, and let's just imagine a Gaussian surface. So if we have a Gaussian cylinder, what would it be? It would be D. We know we have symmetry, so as long as we're on a cylinder that it has its same axis as the dielectric cylinder, then D is going to be constant, and the circumference is 2 pi little r, because we have a variable size Gaussian cylinder, times L. And what does that equal? That's the left side. That's the integral of d dot dA. And the right side is just the free charge, which is just lambda F times L. All right, so cancel L, and you find that the displacement equals lambda F over 2 pi R. And you say, now wait a minute, is that for inside this dielectric cylinder or outside? It's for both. It doesn't even matter, the dielectric cylinder. We'll use that later when we're getting the E field. But for this itself, it's for both R is less than big R and R is greater than big R, inside and outside. So now we have the displacement. If I want to make it a vector, it would be out, if you feel better to see it as a vector. Right? So it's just like doing Gauss's law for a line of charge. It's this field that just follows this standard equation, 1 over R dependence, and really doesn't do anything interesting at the interface. So now let's use that to get the electric field. That's the thing we really want. We have an expression for D that applies both inside and outside, but of course what we really want is the electric field, or maybe we want the polarization. So what we've got to do is just now use our definition of D. D is epsilon naught E plus P. So let's first look outside. So for the radius R greater than big R, also known as outside the dielectric, then D is epsilon naught E plus the polarization. What's the polarization outside? It's 0. There's no dielectric. We're outside the dielectric. No polarization outside the dielectric. So if we solve for E, we see that E is 1 over epsilon naught D. That's a D, not a P. And then if we just plug into what we had for D, we get that the E field outside the dielectric, R bigger than R, is lambda F over 2 pi epsilon naught R, which is exactly what we expect from Gauss's law for a line of charge, right? Lambda over 2 pi epsilon naught R, R hat. So our displacement field on the outside, everything worked out fine. Now let's look inside. R, little r, less than big R inside. All right, so again, we're going to say D is epsilon naught E plus the polarization field. Okay, well, let's solve for E. So E, bring it over here, it becomes, bring the P over here, it becomes the E field is 1 over epsilon naught times the D field, the displacement minus the polarization. And you say, okay, we have D. We got that from the old Gauss's law for D, but now we need a relationship between P and E. We are right back where we started with the slab. we know that the electric field creates some polarization, and the polarization reduces the electric field. Therefore, the polarization reduces itself. That depends on the electric field. We're calculating the electric field. We're back in the circular loop. How do you figure that thing out? You could go with a microscopic theory, or you could just say this is a continuum. Let's just assign a variable to it. Let's do that on the next board. For most dielectrics, the P, the polarization generated, is proportional to the field applied, or to the field in the material. So we just define it with a constant, right? So we say that P is epsilon naught. That's there so that this constant, chi e, can be unitless. Right? And that constant is called the electric susceptibility. And the name is clear. It's how susceptible the material is to being polarized when it has an electric field inside of it. Notice I'm not saying applied to it anymore. Electric field inside of it. If you apply a field, it can be reduced by the polarization, and then the polarization is reduced, et cetera, et cetera. It's really just, that's the polarization you get when there's this much E in it. Once we got to the advanced part, we stopped writing applied and internal and external. Okay, so let's now use that. D is epsilon naught E plus P, therefore it's epsilon naught E plus epsilon naught chi E times E. So now you can see things are starting to simplify, and you get that the displacement field is, we pull out epsilon naught, and then I usually write it, the 1 plus chi E times E. So we have a simple linear relation, or a proportional relationship between the polarization and the electric field. That's the electric susceptibility, so that word kind of makes sense. And then also this, we have a proportional relationship between the displacement field and the electric field. And then we also give this a different name. This is just epsilon. So there's also a simple proportion between the displacement field and E, and that's just the permittivity. Okay? That's why when you see it with a naught, epsilon naught, the permittivity of free space, how much field is permitted to be formed due to a charge, right? So this is the permittivity of the material. How much field does it get due to a charge? And so you can see we now have a few constants we're keeping up with, right? There's how much P, polarization, can form. There's how much D, displacement field, can form. And then there was that dielectric constant. How much is the electric field reduced by K? So I like to always have one equation, I usually memorize it, that has all of them related. Is the dielectric constant, you can see, is this 1 plus chi E, right? If you were to take that away, this would be E, which equals epsilon over epsilon naught. So if you ever want to double check your understanding of them, they all fit together like that. So when we did all this, did displacement help? In this example, you could argue it didn't really help that much. We could have just written Gauss's law with epsilon naught E plus P. But as you get to more and more complicated examples, when there's curls and all this stuff, it's helpful to have other fields to use when things get more complicated. But anyway, that's the nature of how to do dielectric problems in electric fields, at least highly symmetric ones that we can solve with Gauss's law. I forgot to finish the example. We did all that work, and I forgot to finish it off. So we had let's see, a wire with lambda free charge density on it. We had this dielectric material making a ring around it, and we calculated the displacement field was lambda free over 2 pi r hat from Gauss's law. And it's, of course, it's the same outside and inside. That's what the displacement field is useful for. But now we know that D is the permittivity times E. So we just have to divide through by the permittivity, and we get that the E inside equals lambda free over 2 pi r epsilon. And then we're done. So that being just a property of the dielectric, you could write it in terms of K. The dielectric constant, you could write it in terms of the susceptibility if you wanted. Now we're done.